Welcome to our business track of the Data Science Salon YouTube channel. This is a presentation by Mario Vinasco, Director of BI and Analytics at Credit Sesame, and his talk presents key insights that make AI and ML useful for marketing and demystifies the core technology while illustrating his team's case studies. Enjoy!
Hello, good morning or good afternoon. My name is Mario Vinasco. I am currently Director of Analytics for a fintech company in San Francisco, California, where we manage a marketplace for financial wellness. We match customers to the best financial products we can find for them, and we also recently acquired a digital banking business that is going to help our users to improve their credit score. In this talk, I'm going to present some use cases of machine learning and how we use that in marketing analytics, how we have used these models in combination with other statistical methods and tools in order to better understand our customers, who is going to churn, who can we cross-sell to, and how we can attribute any marketing incentive or initiative to a lift that we observe in our subscriptions or our improvements in terms of credit applications and others. I am going to give you a very brief introduction to artificial intelligence and machine learning is or are to derive one of the key insights, one of the key intuitions behind these tools. And these tools are being commoditized, but it's very important to understand at least the basics of how they operate and work so we can really exploit and get the best of these tools. We will move into some of the models that we have used and finally the use cases. Because this is a recorded session, Q&A will be submitted offline, but I'll be happy to connect with you via LinkedIn or other social network or email. It's really incredible that 5-6 years ago, computer vision was really in its infancy. It was very hard for a computer or very expensive to be able to classify correctly images of cats and dogs. By now, this is artificial intelligence 101. Any good course or any good book on artificial intelligence starts with this, how we do that. And this is trivial now to the point that we have autonomous cars and image recognition in medicine that are extremely accurate. But how did this happen and why is it important to know? Let me illustrate that point. Some of the key elements that researchers 6-7 years ago did was to start converting these images into numbers. As you know, computers do not understand textures or colors. They understand numbers. They divided these images in pixels, let's say 200 pixels vertical, 200 pixels horizontal, and then now we have 200 times 200, that's 40,000. They divided these images in 40,000 pixels. Each one of those pixels was then characterized by the 3 primary colors, the amount of green, red, and blue. Now we have 40,000 points times 3 as 120,000 points. Very neat trick, but as you can imagine, this thing grows exponentially because not only you have 120,000 data points per image, but you have thousands of images that you need to correctly classify. They feed these numbers through what we call a perceptron, which is nothing more than a simple multiplication and addition of those numbers. The X numbers that you see on the perceptron are each one of those 120,000 data points that represent the pixels of the images, and the number W's are the numbers or parameters that the network or the perceptron or the computer needs to learn. Therefore, the name machine learning. Through iteration and calibration, the computer will learn what those number W's are, such that when you multiply that times the X numbers and you sum them up, you produce a 1 or a 0, depending if the image is a cat or a dog, and then you iterate until the number Y gets closer to the desired target. Obviously, a perceptron is not going to work very well for complex things like image recognition, but when you stack them up and you have many layers of those, that's where the magic of machine learning, and specifically, or more specifically, artificial intelligence and computer vision in this case happens. Somewhere inside that network, the recognition of these images happen almost magically. And one thing that is important to highlight is now we don't have to worry about those architectures. How many perceptrons, how many layers, how do we connect them? Those architectures and the solution to those problems have been commoditized. Any good cloud service provider, Google Cloud, Amazon, Oracle, any of those, Microsoft, they come with those models pre-built with the hardware and the software installed for us to do that. And again, it's commodities now that we can use to train and use. So we no longer have to work about the inner workings. But I'm telling you this because it's very important to understand how those algorithms get calibrated and understand some of the concepts behind it. So now imagine that instead of cats and dogs, what we have is, let's say, our customers. We have the customers of the company, our subscriptors. And we are very interested in learning how those subscriptors, how many are going to continue, renew their subscription, how many are going to churn, or how do we manage attrition. And instead of the pixels and the colors of those pixels, what we have now is history of these customers, behavioral, demographic, psychographic, how many times they have been in our website, in our app, what products they have bought in the past, what is the pattern of subscriptions that they have, etc., etc., etc. When I collect all that information, and let's say I collect 60, 70, 80, it's common to collect 100 variables or more per user. And when I looked in the past over a period of time and tag them, this customer continue, this customer churn, this customer continue, this customer churn, what I have is a classification problem very similar to the cats and dogs. And again, I have the 0 and the 1 representing churn instead of a cat or a dog, and I have behavioral data instead of pixels. If I feed that data through my neural network, that network learns the correct, or for the most part, the most approximate weights that predict who is going to churn. Imagine that I train my model. My model gives me decent levels of accuracy in terms of the prediction, and I then score my customer base as it is right now. I train my model in past data, learn to classify those things with decent levels of accuracy, meaning few errors. Then now I score all the customers that I have live. And if I wait a sufficiently long time, let's say the model was being trained for a window of 30 days or 60 days, and then I weight those, what we will see is when we rank those customers from high probability to low probability to churn, we will see that indeed the true churners will be concentrated towards the top. And when I make a call, when I make a cut at a particular threshold, and I say anyone that is above this threshold, I am going to assume that they are going to churn in 30 days, we will see that indeed many of them will churn. Of course, we will have what we call true positives, meaning people indeed they churn, and false positives, and obviously we will miss some people. No machine learning model is perfect. Computer vision is definitely more advanced, and they are getting to levels of 99.9 levels of accuracy, especially like in medical images and others. In marketing, we are happy with a 75, 80% level of total accuracy. Then the question is, how is a 75 or 80% model, accurate model, good for me? You certainly will not board an autonomous car with 20% chance of crashing, right? Certainly you will not do that. But in marketing, those levels are pretty good, I would say. Imagine this scenario. Imagine that I have a subscription business. My churn rate is 10%, just to make things simple, per month. And then I am going to design a campaign, marketing campaign, or an incentive to prevent churn. I'm going to send a coupon, a discount, you name it. I am not a marketer. I am a data scientist. You come up with the idea, and then we are going to target those people. If you don't have any model, and then you target your entire user base with that promotion, you will have to target 100 people to catch 10 that are going to truly churn. Meaning you have to pay for 10 exposures in search or in Facebook or Instagram or any social network. You pay because you have to target 100 people, and then randomly you will catch the 10 that are going to churn because 10% is your churn rate. randomly speaking. Now imagine that you run the model, you rank people from high probability to churn to low probability, and then you cut at the 80th decile. Or in other words, you target the two top deciles, the top 20% of the customers. Now, for every 20 customers that you target, you are going to get 5 or 6 of the true churners. So imagine that difference. I pay for 100 to catch 10, or I pay for 20 to catch 5 or 6. It's an improvement of 4, 5, or even 6x in the efficiency of my marketing investment. And that's why these models, machine learning models, are so useful and so powerful, because it allows us to target more precisely and catch more of the people of interest in a much reduced base. Obviously, I can lower the threshold, catch more people, but at the same time, then I will have to target more. And that's the threshold, that's the trade-offs that we have to negotiate with marketing. And in many cases in marketing, we don't train this model in computer vision is in terms of accuracy or precision. In many cases, what we do is we optimize for recall. Recall is how many of the true positives or the true churners we catch when we make that call or that cut of the threshold that we want. That's the insight, that's the intuition that I wanted to highlight, and that's what I told you some of the basics about these models. Now let's see some other advancements in terms of machine learning. It's a very active area of research. We are currently using some of these, specifically embeddings, are mathematical representations of entities that are coming very handy and are very powerful to classify, associate, and help in the overall predictions. And there are many others. We are not going to go into any of these details, but I wanted to highlight some of these areas as very active areas of research. Marketing attribution is the first use case that I want to go through. And if we have time, we'll go through cohort analysis. Some of the power of the machine learning models don't come necessarily with the straightforward applications, churn, cross-sell, or the others, but come when you have them in combination with other methodologies, other algorithms, specifically simulation, in statistics, or other machine learning models for that matter. That's when you realize even more power of this. And again, you don't have to worry much about how you train those models. Those algorithms and those architectures are commodities by now. You have to understand how to use it. It's up to you how to work with data scientists effectively in order to deploy those in the correct ways. We have recently a combination of marketing initiatives to improve the subscription to our banking business, to attract more customers and have those customers to fund. And you can think of all the initiatives, interventions, and campaigns that are out there. We did it. We did social network, we did search, we sent incentives, we sent rebates, we sent sweepstakes, we sent in-app messages, and you name it. Many of those were A/B tests. And obviously, when you have an A/B test, you understand if the test works better than the control or not. We saw an overall lift. What we didn't know and we could not establish is what is the contribution of each one of those things to the overall lift that we are seeing. If you add all the A/B tests, that's not additive because many of the customers were hit or targeted for several initiatives, and then you cannot take credit multiple times for the same conversion. But each one of those contribute a little. Attribution algorithms and attribution methodologies are really hard. We have like MMN, marketing mixed media modeling, and others that are top-down, require a lot of data for longer periods of time, very difficult to train, very difficult to interpret, and very difficult to deploy. We needed something more practical, even though it was not as elegant as MMN. And what I started thinking is, why don't we use the models that we have? We have machine learning models. We know how to do a statistical simulation, and we have visualization tools to do these things. We have a large user base that receive all the different combinations. Again, these models become very, very useful when you have different things. If everybody receives the same treatment, the model is not going to learn anything. But you have pockets that receive Facebook targeting, pockets that receive mailers, pockets that receive different kinds of in-app or email, and then we have all of these combinations because of all the initiatives. Many were control groups, holdout groups, many were other targeted based on other propensity models, etc., etc. We train a propensity model to understand who, with behavioral data and marketing intervention data, who would convert. In this case, who would subscribe to our digital banking product. That model, as remember the cats and dogs or the chair model, learns the effect or the weights of each one of those variables. We cannot change the behavioral data. We cannot ask a customer simply to love more or less or have a particular credit score. Those are completely out of our control, but we can choose how to target them or exclude from certain targetings. And we use this learning to score all our user base through simulated marketing interventions. In other words, we train the model in historical data with the observed targets and interventions. The model learned the weights of the mailer, of the money incentives, of the emails, of the in-app, and then we remove that, and then we re-score everybody again with simulated scenarios. We had 5 marketing interventions. Those 5 marketing interventions, all the combinations would be 2 to the power of 5, or in other words, 32 different scenarios, and then we score all the users in each one of those 32 scenarios. We had then 32 predictions for each user according to the model. Again, the model is not perfect. The model has noise. The model is not 100% accurate. The model was about, because the objective here was to maximize the learning of the algorithm. We got an accuracy of like 90%, which is very good. The problem with that is that it's not very good for predicting future data that we haven't seen yet, but it's very good for learning what we had in the past. And because we are going to score the same customers with the same behavioral data, only with simulated scenarios, this was pretty good for us. The problem with these things is usually that in any prediction model, what you have is a highly skewed curve of predictions, meaning that most people will be scored in the lower probabilities and probability of prediction bands. Very few people will have scores in towards the right of the axis level. You can see that the high bar is almost at 0% probability, meaning that the models cannot really distinguish that well. But it distinguishes and has some discriminatory power towards the right, meaning that some of the people are predicted with some much higher probabilities than others. And that's important. If you have those predictions for the scenarios across all the distribution of the users, how do you decide which scenario works best? In other words, what combination of marketing initiatives works best than the other if all that you see is a long tail distribution like this? If you take the simple average of each one of those and compare it, it's going to be highly skewed, because a simple average is very sensitive to the outliers. It's very sensitive to the zeros, and it's very sensitive to the high scoring people. And it's not a true representation of a distribution like this. So we have to do a simulation on top of the other simulation that we already have in order to get the true average. And what we did is we did what is called in statistics a bootstrap method, or sampling with replacement. In other words, we had the distribution of each one of those 32 scenarios of how the customer distribute, but we start drawing, take an average, replace, take another drawing, take the average, replace, take another drawing, and we do it many times. We do it 500 times in each scenario, meaning that we have 500 averages in each scenario. And then those 500 averages, by by the power of what is called in statistics the central limit theorem, which is a mathematical construct that is very brilliant. There is a property of all those averages. When you take a sufficiently large number of averages of those distributions, the average of those averages is a normal distribution, which is very pretty, very good, very interpretable. Again, we took each one of these distributions, each one of those 32 each one of those 32 distributions, we resample those with replacement 500 times, and we got a distribution of those 500 averages. When we plotted this way, we could start seeing which scenarios work better on average than others. You can see that the top scenario, the yellow one, works better than the green and the others, but the green work better than the blues. And that's how we determine which scenario, and again, each scenario represents a particular combination of marketing initiatives work best on average. And based on that, we were able to rank, prioritize, discontinue some of the initiatives, and expand and accelerate some of the others, which was a very powerful insight for the team. Again, the power of this attribution model and the simplicity of it was using machine learning model, some simulation, and some bootstrapping statistical, again, another simulation on top of that in order to come up with those. These findings guided the next round of investment in marketing and was extremely well received by the executive team, was extremely well received by the marketing team, understanding how those different initiatives work or incentives work in combination, which is, again, the whole point of marketing attribution. Another very common use of machine learning models is cross-sell. Cross-sell is a much more straightforward application of machine learning models. In particular, what we would like to understand is if you have customers that are using some of your products, who are the people that can convert to more value, premium, better, more value-added products from their customer base. Cross-sell is something that has been around for decades. All marketers are very familiar with the concept. When you score your customers, very similar to the churn model, very similar to the cats and dogs prediction that we have, in terms of you look at the past data, you look at who has converted from lower added to higher value added products. You train models based on the behavioral data, also with the purchase data. Then you start seeing these curves. One way to look at the cross-sell model is when you plot the actual conversion on the vertical axis to the predicted score or the propensity to convert. And then what you would see usually is a curve like that. Notice that notice the upper right corner. When the model says that the propensity to convert is 80 or 90%, you don't see 90% conversion. You only see like 12, 13, or even 14%, right? You don't see that because those models are not 100% accurate. But what the model is telling me is that the people that are in the right side of the chart, the people over 70% propensity, they convert at 15 times the rates of the left side of the lower propensity. So it doesn't really matter if the propensity is 80% and that cohort or group of people only convert at 14%. What matters is that 14% is 15 times or 14 times 1%. And what matters is that my model can stratify and my model can separate those cohorts of people who are the high conversion people, who are the low conversion, and who are in the fence. And now with marketers, we can start the conversation. What do we do about them? As a data scientist, I can identify them for you. I can put them in each one of these three bands. You tell me what to do. Do we go after the high conversion? Do we offer them incentives to accelerate that even more? Or do we think that that's good enough? They are converting well organically, and maybe we focus the incentives and the initiatives on the people that are in the fence. Obviously, the people that are in the left, we probably would not like to spend money because they are not going to convert pretty much no matter what. It would be very expensive to convert them. Then we can focus either in the middle or in the high. And that's the discussion that we have typically with marketing, how to target them, what messages, what incentives, what combination of these things once we are able to target that. Again, that's the combination, that's the power of these predictive models. That's what companies like Facebook or Uber or Credit Sesame, my current company, we spend so much time and so much effort training these models, using them, deploying them, retraining them, because it gives us those insights. It gives us those targets. It can identify those customers. And again, not necessarily being extremely accurate, but being able to divide, separate, that's what counts for marketing. I'm going to very briefly show you another area where we have used this type of methodology, not exactly machine learning in the prediction traditional way of doing it, but cohort analysis is also a very important analytics tools in marketing, and specifically what we do. A cohort is simply a group of users that are identified by a common feature, a common variable, or a common characteristic. Users that sign up at the same time through the same digital channel, or users that are in a certain age bracket, or users that behave a certain way. You can construct cohorts in any number of ways you want, as long as they share the same characteristics. And then the key with cohorts is that you measure them not in terms of calendar days, not in terms of the dates, the actual dates of the calendar, but in terms of the number of days since the event, the conversion event happened, regardless of the date where they occur. Meaning that if I am in the same cohort as any one of you, but you sign up, let's say, a month earlier than me, day zero for me will be the same day zero for you, because what we are interested in is that conversion curve. We want to see how long does it take that curve to reach maturity, how many days, and what is the level of maturity that that curve or that cohort of people reaches. Again, defining the cohort as any way you want, any way you need to. And then once you do that, what some of the algorithms that are derivatives of the traditional machine learning models is they are very good at learning the representation, the mathematical representation of that curve. It's not what you observe, is what the observations imply for the future. And then these models are able to produce the curves that you see on the screen with the uncertainty bands. And again, what these curves show you is that for different cohorts, they have different levels of maturity or saturation of those curves, and how long does it take for these curves to reach that saturation. As I mentioned, choosing the cohorts might be tricky. Most of the time, what you do is to establish the cohorts by the date of the sign up, the date of the user registration, and so on and so forth. But we did one additional trick. As we have trained many propensity models to either cross-sell or convert or sign up for this, we use the features suggested by the prediction model to do the cohort. One of the byproducts of modern machine learning algorithms is what is called feature importance. It tells you of the 80 or 90 or 100 variables or features that you feed into your model, which ones are the more predictive. We took the more predictive ones, and then we combined. In this case, were people that were using the app a certain number of times, people that were doing applications to credit products a certain number of times, or have received and opened certain emails. Then we cohorted people that way, and then we measured these curves again, and then we understood which cohorts were converting much better, and start designing incentives to either accelerate or raise that level of saturation in those curves. With those case studies, I would like to thank the audience, thank the organizers for inviting me to share this with you. I'll be happy to connect with you via LinkedIn, via email, answer any questions. And just as a wrap up, what I really wanted, the key takeaway for all of you was to take some of that intuition of how these models work, how these models can work very effectively in combination with other analytical tools, and how can marketers and executives have a productive dialogue with data scientists like me in order to get the best out of these models, understand their limitations, understand the noise, the inherent noise that they have. But again, even with that, how those models can be very, very powerful rather than the slice and dice that we used to do since the 90s. Thank you very much, and I hope to see you very soon in another talk like this, hopefully in person very soon when we return to a semi-normal in presence, because I enjoy these events very much. Until then, appreciate your attention very much. Thank you.
That was a presentation by Mario Vinasco, Director of BI and Analytics at Credit Sesame, on great insights that makes AI and ML useful for marketing, along with case studies from his team. If you enjoyed this presentation, please don't forget to subscribe to our channel below. Thanks!